Okay, in my previous video, we talked about supervised learning, right? So there we also talked about two different kinds of problem we can solve using supervised learning called regression problem and the classification problem. In regression problem, we basically we are predicting some things like some numerical values, right? And in the classification problem, we are basically predicting the class output from a finite set, right? So we also talked briefly about linear regression, right? Where if you have a data set something like this, the idea behind linear regression is to fit a line to the data, correct? And while discussing this one, we talked about this candidate admission data set, right, where we have lot of independent variables like GRE score, TOEFL score, university rating, something like that, and based on that we are basically predicting the chances of admin, right? That's our goal. So today we will see how the core algorithm of linear regression works. Okay, we will try to do some kind of mathematics as well behind this. Okay, so to do that, what I have done is actually I have written the whole math stuff in a software called Bamboo Paper. Okay, so initially I was thinking like I will do it live, but it was not. It was actually not adding any value. It was more time taking. That's why I thought of I will present it something like this. Let me know if it is not intuitive enough. Then I will try to find out some other ways to present it. Okay, so this one also I have exported as PDF, so these two are same content. I'll be using this one to for mainly the presentation purpose. Then we will see this one if we need to back reference anything over there. Okay, so before we enter into the core algorithm part of linear regression, let me give you some notations first. Okay, so we will see x as input variables or predictors or independent variables. That means whatever, if we just map to our this data sheet, that means this columns marked as orange color will be our input variables or the independent variables. Okay, and we will denote y as a output variable or response or dependent variable. In this case it will be our chance of admin, this column values. Okay, now we will say n is our total number of observations. That means the data which we'll be using for training purpose. Okay, the total number of records. Now generally in linear regression, we also discussed the same thing in our previous video as well. We have both the dependent variable and the independent variable together as a training set, right? So that the learning algorithm can learn from it. Okay, so the capital N will be basically telling us how much of the data we are using for training purpose. Suppose you are using the first 34 as a training purpose, so N will be the 34. Okay, so like this, the rest of the data we can use it for prediction purpose. Okay, to check how the model is working. Okay, so p will be our number of features. Okay, so as I said, independent variables are called features in machine learning. So this will be our number of features. So if we map to our data sheet, it will be 1 2 3 4 5 6 7. So the value of p will be 7 in this case. Okay, let let me introduce you another notation. We'll say small x, then the subscript will be the observation number and the feature number. Okay, so that means let's say small x11 means the observation number 1, that means we are dealing with first row, and the feature number 1, that means we are dealing with the GRE score, that means 337. Okay, the GRE score of the first observation. So we'll denote something like this. Okay, similarly x12 will be the first observation, second feature value, that means 118. Okay, similarly it's x21 as well, GRE score of the second observation. Okay, second row and the first observation. Okay, so the second observation, the first feature value. Okay, so if we represent something like this, then the single row, let's talk about the first row, we can represent something like x1 x1 x11 x12 x13 x1p, right? 1 1 1 2 1 3 1 4, something like this, right? So this is called actually a row view. Now this is a single row. If we want to represent the whole data set, right, using this same similar notation, it will be something like this. It will be a matrix, right? So the first row will be like this, second row will be x21, then x22, then x2p. That means each and every row will have maximum p values, and each and every column will have the maximum of n values, right? That is the number of observation, and this is the number of features, correct? So you are basically, now you got my point, right, where I am coming to. So basically we will try to represent this whole data set using a vector notation. Okay, so before that, let's talk about vectors. So vectors are very useful structure in linear algebra. Okay, now vector, you may heard in physics like acceleration, right, or the speed, right, as a vector, which has not only have the value or the length, it also have a direction, right? In mathematics, we generally care about vectors in different way compared to physics, but at the end of the day, they both represent the same thing. Okay, so if you see, suppose if I represent a vector v something like this with its endpoint as 3 comma 4, that means from x-axis 3, and if I go up to 4, this is my point, right? So vectors are generally represented as their endpoints. Okay, the endpoint of the vector, so it is 3 comma 4. Now the length of the vector will be this length, right? So according to Pythagoras theorem, if you just apply the c square equals to a square and b square, then we'll get the length of the vector, right? Now vector has lot of properties, but we will try to discuss whichever is needed for this tutorial. Okay, so if we talk about twice of a vector, that means the length of the vector will be twice of that vector v, but the direction will be in the same direction, correct? Now if we want to add two vectors, right, so we can add something like this. First the initial vector, then when the a vector ends, suppose I want to add a and b, where the a vector ends, from there I will append the ab vector, then add the initial point of a and the ending point of b. So that vector will represent the plus of a and b. Okay, so using this notation, if I define a unit vector along x-axis as I hat and along y-axis as j hat, then using these two, we can come up with this formula, right, of v, where the v will be basically I into 3. That means because we are going 3 times over here, then we are going 4 times over here, right? So 3i will be this vector until this point, and 4j will be this vector. If we add those two vectors, we'll get v, right? So this is what exactly what I am doing over here, correct? So in mathematics, so this is what we have discussed now, like physics. um, Physics, we have seen vector as it is, right? So in computer science, basically the vector we talk about as a matrix. Okay, a single row or single column matrix. Okay, so generally when we represent vector, we represent it as a single column only, but row vectors are always possible. Okay, so and what will be the entry of those of that particular column matrix? It will be a endpoint of those of that particular vector, so it will be 3 and 4. Okay, so let me introduce another term over here called transpose of vector. So when we do transpose, right, so what we do basically, we basically convert the rows into columns and the columns into rows. So for an example, if I give v as 3 4 vector, so the v transpose will be, it will be it is a column vector, right? It will be changing as a row vector like this. Okay, simple stuff. So with this concept of vector, let us try to uh, implement this x as a vectorized form. Okay, so for that, what I'll do here is I'll go back to the X here so that we will back reference here. So let us introduce another notation here. Okay, so if you think about it, all the rows of X over here, right? So let me add the formatter. So all the rows of the X over here, right? This X11, X12, X1P. If you see it here, the first subscript is not changing row wise. Only the second subscript is changing because our feature is changing over there till the P, right? So if I give a notation something like xi, which will be representing as a column vector as xi1, xi2, xip, that means generalized form of this all this row, correct? Then the transpose of this one will be, we will just convert this column to rows, right? And if you think about it, this is basically representing each and every row of X over here, correct? So I can write X something like this: x1 transpose, x2 transpose, xn transpose, right? So this is called a row view representation of the features or the whole data set or the training inputs. Okay, now there will be a column representation as well. So if you if I just add another notation over here, zj, what it is doing, suppose for each and every column, if I represent it as a vector, okay, so what will be the content of zj? If you see it over here, the second one in this case will not be changing because we are basically dealing with a single feature, right? The changing will be the observation number over here. That's why 1 2 till n, correct? So each and every z I'm talking about here, suppose GRE score, right? So I'm basically representing GRE score column as a vector. So that's why my j is not changing over there, only the based on the observation number 1 2, the first subscript is changing over there, right? So if I do it, if I represent X with zj, then it will be like z1, z2, zp, correct? Because for each and every feature it will be a column vector. Because if you see here over here, I have not transposed it, right? Because it itself is a column vector and it is representing a column as well. While in the previous case it was representing a row, but my vector assumption was the initial notation was in column format. That's why I transpose it. Okay. So this Z view is called the column view of the inputs. Okay. So let's move on. Okay. So now if we talked about the representation of the inputs, right? The independent variables. Similarly, the representation of the output or the dependent variable will be similar way, right? It will be just a single column vector with these elements y1, y2, yn, correct? Now this leads us to a two important stuff in linear regression. Okay, so in simplest term, the linear regression can be a single feature, okay, and then single output. And in most complex term, and which will be the most real world scenario as well, we'll have multiple features and then output. Okay, but to do the math, okay, we will first talk about simple linear regression so that we'll understand the math in easiest way. It will be helpful to understand the more complex stuff like multiple linear regression. Okay, so if you see, the linear regression can be subdivided again to simple or univariate linear regression or multivariable linear regression. Okay, so now let's transform the whole concept, the vectorized input form, to a very simplistic way. Now if you see, for a simple linear regression, I have, if I just go by the column representation of it, I have a single column, right? Let's say GRE score, correct? So it says Z1, correct? Now according to Z values, let's go back to our PDF. So how we have represented Z, so it will be x11, x21, xn1, correct? So this is the one I have written over here. We are talking about all the values belongs to the first column. Okay, now if I further simplify this notation, because we have only a single feature over here, so I can write it down as a x1, x2, xn, right? And we already saw our y as y1, y2, yn, correct? So in simplest term, we can think about the whole data set for the simple linear regression as this key value, this value pairs, right? x1, y1 value pairs, right? So if I just go back to this one, so this one x1, this will be y1, this will be x2, this will be y2, correct? So this is how I am visualizing the data now. Okay, so let's move on. Okay, so we are now slowly entering the linear regression and core algorithm. So before we enter that, generally when we get a data set, right, and we are planning to implement linear regression to see how it fits and how the prediction works, generally, right, we ask these questions. So suppose I am talking about in terms of our data set. So first question generally arises: is there any relationship between GRE score or and the chances of admin? If there, then what will be the strong, or what will be the if the relationship is there, how strong it is basically? Okay, and the most important question will be, is that relationship is linear or not? Okay, so if there is any linear relationship exist between them, then only linear regression will be the proper choice for implementing the machine learning over there. Okay, so let's talk about the math. We will do it over here. Okay, so as you have seen it before, so the main goal is to fit a line, right, to this whole data set. So that means we ultimately, at the end of the day, our model will be a equation of line, and we already know from our basic math the equation of line is y equals to mx plus c, right? Now where m is the slope of the line. Slope means if I want to go from one point to another point, what is the y value changing? Okay, and what the y value, the change of y divided by the change of x. We'll discuss slope in detail in latter part of this tutorial as well. Okay, and the c is the intercept, right, over here, like where it is intersecting with the y-axis. Okay, in machine learning, this m and c are called parameters or coefficient of the model. Okay, and if you see it over here, we are not doing any fancy thing over here, right? We are doing just the simple math over here. Okay, so this fancy terms we'll always see in machine learning. So let's go back, go to the next page. Okay, so if I just write this particular equation we discussed over here, so y means our output, that means chances of admin. X means our input. In this case, as we are talking about simple linear regression, it is our GRE score, right? So we can write the whole equation something like this: chances of admin equals to m into GRE score plus c, right? So if I come up with this kind of equation, right, so if I enter GRE score, this model will be able to predict the chances of admit, right? So now we have basically formulated the basic of our goal. Okay, so now I can fit thousands of line to this data, correct? I can fit thousands of line. A line could be from here as well, here as well, right? So which one is the best line? Okay, so to do that, we need to come up with an idea of the goodness of fit, right? So basically we are trying to determine how good the line is fitting the data. Okay, and now the measurement of goodness we need to come up with, right? So that means we need to come up with a error for each and every line representation and choose the line which has the minimum error. Okay, that's the concept. Now I am slowly entering the concept of least square over here. Okay, so let us define our error function first. Okay, this is the epsilon. I just give it a name. Okay, so if I define epsilon with this below criteria, something like this, so if the line pass through the data point, my error is 0. That means if you see in the left hand side diagram, I have just taken 3 points over here. Okay, so this point, these green colors are the data points we have in our data sheet. Okay, and this is the line we are basically saying will be the fit of this data, right? Mm, Now, if you see this line passing through the first point, that means for this point, the error we will consider as 0 because it is passing through that point. Correct? Now, we'll also determine, or we can think of it error as cannot be negative. Okay. Now, why I am saying that? Let's talk about these 2 point. Okay. This y2 and y3 point. Now if you see this line passing below the y2, okay, and this line passing above the y3, okay, it is not passing through any of them. Okay, now at the simplest term the error could be the difference of these two values, y, the predicted value, minus the actual data point value, yi. Okay, so now if you see, in this case, the y value, y minus yi, will be negative because this is going below the actual data point. And in this case, the y minus yi value will be positive. Okay, but both of this case, the line has an error. Correct? So that is what I am trying to say it over here, that the error cannot be negative. But if we just take y minus yi as a error function, then we are basically dealing with the negative values. To overcome this, we are taking the square. Okay, and if I draw a square based on this size of this side, okay, if you see, I can draw a small square for each and every data points. And now if I rotate this line to fit it properly, you will see this squares will be, if I rotate this line left hand side, that means anti-clockwise, this square, the area of this square will be smaller, but this square will be bigger in size, right? That means we have to come up with a line for which all the small square, the summation of the square errors will be minimum. Okay, so that will be our goal. I think that could be one of the reason this is called a least square as well. Okay, the cost function, generally we are talking about a cost function here. Okay, now so we have defined a error function over here, and but that too for a single point over here, right? We have to do it for all the points, the total error. What I need to do, basically we need to add it up. Correct? So this brings us to this notation over here called the summation. So that means our total error will be summation of all the data points. If you see 1 to n I have taken of all the errors. Correct? So if we do the math now, so we already know epsilon. So I'll just go to our PDF and keep it over here. Okay, so this one is equals to y minus yi then square, right? So I have just replaced this one with y minus yi squared. Okay, and to save space, I'll assume this notation, this normal summation notations will be similar as I equals to 1 to n. Okay, now if I just do this square term, right? Now in this square I know what is y, correct? Because we are basically calculating y for each and every value. If I just go back to my PDF again, so each and every data point I am determining the y. So that's why I have replaced y with mxi plus c, because y equals to mx plus c. So xi will be the for each and every data point. Correct? So this equation is becoming like this. Okay, and if I just do the simple math over here with a plus b plus c whole square, then I'll come up with this formula. So I have just expanded it like this. Okay, so now after this one, so if you see, I can just distribute the summation over here like this. So it will be summation of m square xi square, then summation of c square, summation of yi square, similar way. Okay, so we'll come up with this equation of e over here. Okay, so let us do the further simplification of it. Let's go back to the next one. So what we'll do, we will take this summation xi square yi square, and then summation of xi, summation of yi, and the summation of xi yi as a separate variable. So that is what I have done it over here. So I have taken variable alpha, beta, gamma, mu and theta. Okay, I just replace them in this equation. So this is our initial E equation, right? So after replacement it will be m square, then beta, then summation of c square. I have not given anything over there, right? Anything over there. Then summation of y square will be becoming alpha, similar way, correct? So now if you see, summation of c square is still exist, correct? And if you see it over here, I have given an assumption that summation will be as summation I equals to 1 to n. So that is what I have written it over here. And if you see, c is a numeric value, right? So c can come outside of the summation, so it will becoming sum of I equals to 1 to n. That means the total number of observations. So that's why the value will be n, correct? So our final E equation will be coming something like this. Okay, so now we know an equation of E over here, right? Now our goal is to find this M and C values, correct, for which E will be minimum, because our end goal is to minimize the E, correct? So for that, this particular problem is now becoming as a calculus problem, correct? Because if we know about calculus, using derivative, okay, first order and second order, we will know what will be the minimum point of a particular function. Okay, so let's talk about that. So we are introducing a new term called derivative, right? So from our initial class 10 math, we know derivative is like it's a slope of the tangent line, right? So if we talk about a curve, so for each and every point on this curve, if I draw a tangent, the slope of that tangent line is basically the derivative value for that particular curve, for that particular point, right? So two important term over here is the slope and the derivative. Let's talk more about them. Okay, so slope, if you see, I have drawn four figures over here, right? So slope, as I've introduced it before as well, so when you go from one point to the another point of a line, the slope basically determines the change in y divided by the change in x. Okay, so now let's talk about the first line over here, the first diagram. So I am planning to go from this point to this point, right? So I'll be going x direction, this delta x, then I'll be going up, right, the y direction, this delta y. So if you see, from this point to this point, my x is increasing, right? Because the x value here in this point, the x value here in this point is basically getting increased. Similar way, from when I'm going from this point to this point, the y value is also changing and it is increasing as well, right? That's why both are increasing. So if I just give this value over here, so the slope will be always positive over here. That's why it is a positive slope. Okay, now let's talk about negative slope. If you see this, in this kind of line where I want to go from this point, sorry, I want to go from this point to this point, right? I'm still going positive way in the x-axis, right? Because I'm going right side. But to reach this point, I have to go below the initial y-axis point, right? So that means my y values is going downwards, right? Going is basically decreasing. So that's why when it is decreasing, we generally represent it as the negative value. So that's why it is called negative slope. Okay, and let's talk about this line where it is basically parallel to our x-axis, where there also if I want to go from one point to the another point, I am basically the delta x value is getting increased, but y value is fixed over here in this line. So if I just put it over here, the slope is becoming 0. Okay, so this is the any line which is parallel to x-axis will be slope will be 0. Okay, and any line which will be parallel to y-axis, slope will be infinite. Okay, so basically why slope is needed? So slope basically determines how stiff the curve is at that particular point. So that leads us to the fourth diagram over here. If you see, I have given two lines over here, right? Both have positive slope according to this logic, correct? But this guy has more the more slope values, the greater slope values compared to this guy, correct? So that means it is more stiffer compared to this guy. Okay, so hopefully this concept of slope is a little bit intuitive. Let's talk about derivative. Okay, so for that I have taken this equation over here. Okay, so to understand, so as I said previously, let's go to our again. So derivative is the slope of the tangent line, correct? So let's take derivative of this guy. So if we plot this y equals to x cube minus x squared, the the curve will be something like this. Okay, so with this lot of points like 0, 1/3, 2/3, 1. Okay, I have just marked it on the graph, and minus 1, 2. I have not drawn it in the scale. Okay, so if I just take dy dx, which we can represent as y square as well, so it will be nothing but 3x square minus 2x with this kind of formula. I think we have already known from our class 12 math, correct? So if I take the value, the slope at x equals to minus 2, what will be the value? I just need to put x equals to minus 2 over here. So this is becoming 16. If you see, this is a positive number, correct? That means the slope is positive over here. That means the curve is going upwards. Okay, let's take slope at x equals to minus 1. Okay, so there also, if I put minus 1, the slope is positive. Okay, that means again the curve is stiff, but the slope is decreasing. If you see it over here continuously, right, the slope of this point will be far greater than slope of this point. That means the slope is still positive, but the curve is slightly going to the flatter side, correct? This is what the derivative is telling me, correct? So let's take the slope as x equals to 0, correct? And if you see, if I put x equals to 0 over here, the slope is becoming 0. Okay, so that means the slope is continuously gradually decreasing, and it is becoming 0 over here. Okay, let's move on. Let's take the slope at x equals to 1/3. Okay, if I put x equals to 1/3 here, I'll get a derivative as minus 1/3 over here. That means the slope is negative. That means we are talking about this kind of graph, right? So that means what derivative is telling me, till this point the slope was positive, but it was continuously decreasing. That means the curve is going to some upwards point, right? And till this point the curve is reaches its highest point. Okay, then continuously again it is going towards the negative slope. That means again the curve is going downwards, correct? Now at slope equals to 2/3, the derivative is again 0. That means it is gradually the slope is gradually, if you see it over here, the even though the slope is negative, right, because from this point onwards the slope is negative, but it is gradually becoming 0. That means from somewhere again it is becoming less and less stiffer and becoming 0 again. From after this point the slope is gradually increasing again, the stiffer slope, correct? So this is what the derivative is telling me over here. Okay, so now if you see these 2 points, 0 and 2/3, basically the graph is reaching some points. It's extreme points, right? Either it could be maximum points or it could be a minimum points over here. So if you see it from the picture, at the 0 it's actually reaches the maximum point. We generally call it local maximum because because this is not the graph, the graph is actually infinite from these 2 points. So we are only talking about the very specific portion of this graph, correct? And x equals to 2/3, the graph is actually reaching the minimum point over there, right? So if you see it over here from derivative itself, we will not come to know whether it's a maximum point or minimum point. But one thing we come to know is when my slope is 0, either we are hitting a maximum point or we are hitting a minimum point, correct? So to know whether it's a maximum or minimum, we need to do the further analysis on the slope itself, on the derivative itself. That's why the second derivative is coming into picture. Okay, so if we take the second derivative of this guy, it will becoming 6x minus 2, right? So if you see the value of the second derivative at x equals to 0, it is becoming minus 2, correct? Which is less than 0. And x equals to 2/3, it is becoming a positive value, okay, greater than 0. So basically we are seeing when we are hitting the maxima, the second derivative is less than 0. When we are hitting the minima, the second derivative is basically greater than 0. Okay, so basically the second derivative is telling how the curve is going through. That means how the slope is going through. So here the slope is basically going through um, some upward direction, from basically from the positive slope to 0, then negative slope. From the negative slope it is again reaching to 0, then again positive slope. That is what second derivative is telling me. Okay, so that means when we are going from positive slope to negative slope, there is a high chance that we will find a maximum. Okay, and that time our second derivative will be negative value. And when we'll reach from the negative slope to positive slope, okay, there's a high chance that we'll get a minima, and that time our second derivative will be greater than 0. Okay, so as for our error function, so if I go back to our end goal is to find the minimum value of this, to minimize this particular error function, right? That means find the minima of this error function graph. If I just graph it, you need to find that particular minima, right, of this error function. So that means we will be dealing with the this guy over here, where if I second derivative is still positive. And so first we'll do one thing, we will just take the derivative, set it to 0. Okay, and also we'll take the second derivative to check it out whether we are still dealing with minima or not. Okay, so let's do the math. So if you see it over here, so this is what I have written it over here, right? So we now reach a point where we need to take the derivative of e. Now there is another point we need to discuss. If you see, e is a function of m and c, right? Because both m and c is governing the e, the behavior of e, right? The whole graph of e, right? So here we have to take the derivative of e based on both m and c as well. So that's why the partial derivative is coming into picture. Okay, so first we will take the derivative of e with respect to m. Okay, then we'll take the derivative of e with respect to c. So that is what I have done it over here. Now if I take derivative of e with respect to m, the values which basically depends on m will be considering as we will be taking derivative. The rest of the value which do not have any m term will be treated as constant, right? So that is what I have done it over here. So if you see, m square beta will become 2m beta, right? If I take the derivative, this will become 0, this will become 0, this will become 2c theta, right? Because the derivative of m is 1. This will become 0, this will become 2 gamma, correct? So de dm will become something like this, right? So as I discussed before, to get the minima we need to set it as 0. That is what I have done it over here as well. So if I set it as 0, I'll get an equation of m and c, correct? So now while setting this up, we'll also check the second derivative as well over here, if you see, with respect to m. And if I take the second derivative, so of this guy, correct? So with respect to m again, so it will be 2 beta, then it will be 0, it will be 0. So as beta, if you see it over here, is summation of xi square, that means a positive value. Xi means each and every data point over here, correct? If I talk about my data file, each and every point over here, correct? So it is a positive value, so that's why it is greater than 0. That means we are dealing with minimum over here. So from m we got a green signal. Similar way, we will take the partial derivative of e with respect to c as well, correct? So similar concept I have applying over here. So I'll get an equation, I'll setting it as 0, I'll get an equation of c. Okay, so again I will be taking second derivative here as well, and if I take the second derivative on this guy, so this will be 2n, this will be 0, this will be 0. Still n is the number of observations, right? So again this is greater than 0. So that means from C also we get a green signal that we are dealing with minima. So that means we have now two equations of two unknown variable, right? So that means I can solve with for M and C. So that is what I have done it over here. Okay, so what I have done, so I basically taken the M value. Okay, so I basically taken the C value, I think, and then just put it over there in the M equation. We got this final equation of M. And if you see it over here, if I just replace this beta, gamma, mu, theta and n I cannot replace because n is the total number of observation. With all their actual values, I'll be getting this equation. And if you see, this is completely from depend on our data set, correct? We are talking about xi, that means individual data values. We are talking about yi, that means individual values of our training data set, dependent variable. And if you see, this is the interesting stuff, right? When we are doing the training process, our dependent variable also coming into picture. This is where the actual learning is happening, right? So similar way, if you solve for C, you will get this kind of equation, right? So basically we came up with our equation of y equals to mx plus c, where we will be replacing m with this hairy value, right? And again c with these values. We can further simplify these equations, but let's stop over here and let's talk about the fundamental stuff we got it from here. So basically we got an equation of a line which basically have the minimum error, correct? So this line will be our model, right? So now if I just input any x value, it should predict. Okay, so now if you see, we just talked about simple linear regression. That means a linear regression with a single feature. Okay, I know this is a very small step we have taken, but believe me, this, if we understand this one, the next steps will be more clearer, right? So when we talk about mm multiple linear regression, we will basically do the building based on this foundation only. Okay, so it will be it will be easier, right? So hopefully I'm able to give you some intuition behind how this linear regression core algorithm works. Okay, so in next video we'll talk more about multiple linear regression, which will be our real world scenario. If possible, we'll do the math as well, and then gradually we'll be implementing this in different um, programming language called R or something like whatever we feel good, we'll do that one. But if you want to study and understand machine learning, I think this should be the start to understand the core algorithm. Then you can implement in any language, any preferable language. So see you in next video. Thank you.